Direct variation describes a very special kind of linear equation. You'll see that the picture, the graph, it goes through the origin, and when written as an equation, it fits into the form y equals kx. So let's say we have a little friend. We have a turtle, and he can travel at a speed of 18 feet per minute. The table here shows the distance that he can travel while traveling at a constant speed. And so we have that speed right here of 18 feet per minute. So based on the table, after 1 minute, he will have traveled 18 feet. At 2 minutes, he'll have traveled 36 feet. At 3 minutes, he will have traveled 54 feet. And at 4 minutes, he will have traveled 72 feet. This is an example of direct variation. There is a direct relationship between the distance, which could be represented by y, the dependent variable, and the time, which could be represented by x, the independent variable. Think about your vocabulary words. X is the independent variable because it determines how far the turtle is going to travel. However long the turtle has been walking is how far he will have traveled, showing that it's an independent and a dependent variable, and there is a very special relationship between that. Direct variation can be defined as a linear relationship between two variables that can be written in the form y equals kx. It's linear. When you graph it, it's going to make a straight line. There will be no curves, there will be no bends in it. It has two different variables, in this case time and distance, and so they fit in as the x and the y variable. And it can be written in the form y equals kx, and we're going to see next what that k stands for. Over here you can see that k, you can find k, which will, like I said, we'll describe it in just a minute. It can be found by taking the y value and dividing by the x value. So 18 divided by 1 is 18. 36 divided by 2 is 18. 54 divided by 3 is 18. 72 divided by 4 is 18. So here's that equation again. Y equals kx. Y and x are going to represent coordinates, or like as before, values in the table. K is what we call the constant of variation. It is constant because it doesn't change. Think back to our table on the previous slide. Each time I divided the y by the x, I got 18, which was the turtle's speed. In the paragraph before it, it said that the turtle traveled at 18 feet per minute. So the constant of variation, it is the number multiplied by the x. They're side by side. K is going to look like a number. It's being multiplied because they're side by side. It's multiplied by x, the independent variable, to get the y value, the dependent variable. So to check whether an equation is direct variation, you're going to solve for y. And what that means, that's algebra talk. Forget y on a side by itself. Like when we were solving equations, you wanted to isolate the variable. Well, we've got three different variables there. And when you have a real direct variation equation, you're going to have two because k is a number. And so we can't just say isolate the variable. We have to pick which variable we're going to isolate. So that's when you see something like solve for y. The phrase solve for means isolate whatever variable it is that they're asking you about. So we're going to look at three ways to identify a direct variation. And first we're going to look at it in equation form. We want it to look like y equals kx. There's a number that's going to be multiplied times the x, and there's no adding or subtracting on the end of it. It's just multiplying, one operation. So on number one, y equals 2x. If we're wanting to solve for y, we're wanting to isolate y. How do we do that? We undo what's happening to the variable. So what's happening to y? It's being multiplied by 2. I undo multiplying by 2 by dividing by 2 on both sides. It cancels on the left side, so I have y equals x over 2. Now it kind of looks like our direct variation formula, but it's not perfect. If I'm dividing by 2, that's the same thing as multiplying by 1/2. So yes, number one is direct variation. I have a 1/2 where the k would be. So 1/2 would be our constant of variation. On number 2, if I'm wanting to isolate y, y is having 1 added to it, so I undo adding 1 by subtracting 1 on both sides. So y would equal 2x minus 1. And this does not look like our formula because it has that subtracting 1 on the end. So to identify a direct variation in equation form, you solve for y, you try to get y by itself and see, is the x being multiplied by a number? Yes or no? And if it is, make sure that there is not any adding or subtracting on the end of it. So number 1, yes, would be direct variation. Number 2 would be no. If you are looking at a table, when you're trying to identify if it's a direct variation, you're going to see if the variation is constant. Is there a constant of variation? Is the relationship between the y and the x value, is it the same? Is it consistent? So think of your top value as your x's, your bottom values as the y. And as before, we said that k, that constant of variation, is equal to the y divided by the x. If I divide 3 by 1, I get 3. So I'm going to just kind of sketch that right here. If I divide 6 by 2, I get 3. If I divide 9 by 3, I get 3. So as you can see, I have a constant of variation. It's the same for each set. So yes, number 1 is direct variation. I'm sorry, number 3. Number 4, we're comparing speed and time. So speed would be like the x and time is going to be like the y. So when you divide those, y divided by x, 3 divided by 10 would be 0.3. 1.5 divided by 20. Let me go get a calculator for that because that's what y'all be using. Okay, if anything, that gave you some time to write down those tables. 1.5 divided by 20 is 0.075. And then 1 divided by 30, it's going to be something very small, 0.03 repeating. Those are not all the same. So no, this one is not direct variation. So for it to be a yes, when you divide them, it's going to be the same. For it to be a no, they're going to be different. And the third way to identify direct variation is using a graph. When it goes through the origin, yes, it is direct variation. The graph goes through the origin, so this one is a yes. For the second graph, this graph does not pass through the origin. Its y-intercept is up a little bit at +1. So this one is a no. So a recap, direct variation. When you divide the y value by the x value, it's always going to be the same for any point on the graph. The picture of it, if it goes through the origin, it is direct variation. And in an equation, you're just going to have a number multiplied by the x value to get the y. There's no adding and no subtracting. So let's practice it. For each of these examples, I want you to tell whether each represents a direct variation. Go ahead and attempt this. on practice A, you're wanting to isolate y. So you undo what's happening to y, divide by 8 on both sides. So you get y equals 2x divided by 8. That will simplify to y equals 1 over 4x because 2 over 8 simplifies to 1/4. Yes, that is direct variation. On the table, when you divide the y by the x, on the first column you get 0.5, second column you would get 0.6 repeating, third column you would get 1.25, so that is a no. And then on C, yes, it is going through the origin, but it's not linear. It's not making a straight line. It has this curve to it, so it would be a no. It is not direct variation.